All right, let's get going here. Let's start by reviewing what it is that we are talking about for this particular chapter. All right, this is our chapter on alpha carbon chemistry. Okay, so let's remind ourselves we're still talking about aldehydes and ketones. So let's just get an example down here. All right, and if I'm talking about my alpha carbon, use a different color. My alpha carbon. Which one of these is my alpha carbon? Not the carbonyl, but the one right next door, right? So here is my alpha carbon in this molecule. All right, and what we learned about our alpha carbons is that they're relatively acidic. So our alpha carbons are acidic. And what does it mean to be acidic? Well, acids do what? Donate protons or accept protons? They donate protons, right? So if I'm an acidic carbon here, that means that my hydrogen is relatively easy to remove. If we had some base, I'm just going to use generic B for right now. That base can take that proton off. Importantly, then that pair of electrons is going to jump onto that carbon atom. All right, creating what we called an enolate ion. Where I have that negative charge on that carbon. All right, again, we called this an enolate ion. Oops. We took a look at the resonance structures that are stabilizing that enolate ion. All right, you could draw either resonance form here. Okay, and since that alpha carbon is relatively acidic, we can remove that proton, meaning that alpha carbon now has a pair of electrons in my enolate ion. So this enolate ion would play the role of what in a chemical reaction? Is it electron rich or electron poor? It's electron rich with that negative sign. So is it going to play the role of a nucleophile or an electrophile? A nucleophile. So the whole shtick with our alpha carbon chemistry here is that alpha carbon is relatively acidic, which means it can play the role of a nucleophile in chemical reactions. Okay? So if our enolate ion is our nucleophile, our enolate will reacts with electrophiles. And there's two electrophiles that we're going to see in this chapter here, ones that we've seen before. All right, alkyl halides. All right, these alkyl halides, we've seen them play the role of the electrophile a whole bunch, and specifically, what's my electrophilic site in an alkyl halide? If we're talking about electrophiles, we're looking for what? Electron rich or electron poor? Electron poor. So which one of my atoms in this electrophile here is my electron poor atom? Where is my electrophilic site? Yeah, so not the halogen itself. That halogen is actually able to pull electron density away from that carbon atom. So that carbon atom is going to be our electrophilic site. All right. right, the halogen is playing an important role here, both with ducting electrons, all right, but also is going to allow that carbon atom to actually get attacked by a nucleophile, actually accept a pair of electrons, because that halogen is going to play the role of what? The leaving group. Right, so alkyl halides are good electrophiles because they have that relatively electron-poor carbon, and they got a nice built-in leaving group. Okay, the other electrophiles that we're going to see are our carbonyl-containing compounds. All right, so our aldehydes and ketones. All right, and an aldehyde or ketone has what electrophilic site? Where's my electrophilic site in this molecule? That carbonyl carbon. All right, here is my electrophilic site. Because the alpha carbon is what? Not an electrophile, but a nucleophile. So that means that our aldehydes and ketones, they have both that nucleophilic alpha carbon and that electrophilic carbonyl carbon. All right? There's one more that we're going to add to this list here. We'll see this at the end of class today. Also a carbonyl-containing functional group, so we're going to put it down here, are esters. All right, so our alpha carbon is relatively acidic. It can play the role of a nucleophile. And we're going to see two different types of electrophiles that they react with. Our alkyl halides, specifically the carbon bonded to the halogen, and our aldehydes and ketones at that electrophilic site, that carbonyl carbon. Cool. All right, so first one of these reactions that we're going to discuss is what's called an aldol addition reaction. Okay, so if we have an aldehyde or ketone, we're just going to start with our simplest possible aldehyde here. What we're going to do is we're going to add in some NaOH, some base. All right, and that first step is going to be that base playing the role of a base, being a proton acceptor. Of course, the sodium isn't doing anything, so I'm just going to draw that hydroxide ion. And what's going to be my acid here? What did we just say about our alpha carbon here? All right, so that base is going to deprotonate that alpha carbon, creating that enolate ion. And we said that enolate ion plays the role of nucleophile. All right, so in an aldol addition reaction, what is my electrophile? Well, I have a ton of these aldehydes floating around in our solution, right? So this is going to be a reaction where one aldehyde is playing the role of a nucleophile and the other aldehyde is playing the role of an electrophile. I'm going to swap these two. All right, and as we said, it's that alpha carbon that's my nucleophilic site in my nucleophile. That electrophilic site is then that carbonyl carbon of its neighbor. And what do nucleophiles do to electrophiles? They attack, so everybody take a second. All right, we've seen these carbonyl groups playing the role of electrophiles a bunch. Take a second and see if you can't draw in our electron pushing arrows. All right, hopefully we've done this enough that we know that when that nucleophile attacks that electrophilic carbonyl carbon, I can't stop there or I'd be breaking carbon's octet. So what do I also do? Kick that pair of electrons onto that oxygen. All right, so this is going to be now us creating a new carbon-carbon bond. And that means that our products are going to be bigger and uglier than our reactants, right? So this is where counting carbons is very, very important here. I'm going to keep track of my carbons really carefully by coloring them in red here for my nucleophile. So I'll start by redrawing that nucleophilic set of 2 carbons. All right, and now when I draw my new carbon-carbon bond, what's going to be on the other side? My electrophilic carbon, right? So that I've highlighted in blue here. So now I'll color these 2 carbons as well. This is my electrophilic site. I got 1 more carbon off of there. All right. And what else do I need to make sure to include here? What am I missing? My oxygen. I've broken that carbon-oxygen pi bond, but I still have this carbon-oxygen single bond. And not only that, but that oxygen has accepted that pair of electrons, so it has that negative charge. All right, and this thing here, this alkoxide ion, my oxygen with a negative charge, is just trying to kind of stuck, all right, until that water molecule that we created in that first step floats by, and it can deprotonate that water, creating our aldol product. All right, again, this thing is what's called an aldol. Why is it called an aldol? All right, well, we have this aldehyde functional group and then that alcohol functional group, right? We have both of these in our product here, an aldol. Even if there was another carbon over here making it technically a ketone, they still call it an aldol for no good reason. All right, but nonetheless, this is an aldol addition here. Again, we want to count carbons, right? I should have, since I'm reacting 2 of these with one another, each one has 2 carbons. I should have 1, 2, 3, 4 carbons in my product. The other double check that we can do, because again, we're creating these products that are bigger and uglier, is we'll always have the same spacing of these 2 functional groups in our product, since by definition, the nucleophile is the alpha carbon and the electrophile is that carbonyl carbon of its neighbor. We'll always have the same 3 carbon spacing of these 2 functional groups. So just another kind of double check that you can do after you draw your products is making sure you got that proper spacing. All right, count carbons and count how far apart those 2 functional groups are. So this is our aldol addition reaction. We use our base to create our enolate ion, our nucleophile, and that reacts with another aldehyde that's floating around in our solution as our electrophile, creating this aldol product, an aldehyde and an alcohol in that same molecule. All right, so let's practice this. Okay, now we're going to do so with a ketone here. We add in some base, some sodium hydroxide. All right, since this reaction isn't just going to involve one molecule of acetone, but two, one of them to play the role of the nucleophile, the other one to play the role of the electrophile, I think the most helpful thing to do is to draw two molecules of your aldehyde and ketone, and to indicate in one of them you have your alpha carbon as your nucleophilic site, and in the other one you have that carbonyl carbon as your electrophilic site. All right, I think by drawing those two, it's kind of more helpful in terms of seeing what your product's going to be. So everybody's going to take a second and do the product of this reaction. Okay, how many carbons should be in our product? 6. And then I want you to double check your spacing of your functional groups in your product. Make sure they're those 3 carbons apart. All right, since our nucleophile, that fragment appears pretty much as is in my product, I'm going to start by drawing those 3 carbons from my nucleophile, that carbonyl group. And now when I do my carbon-carbon bond here, what must be on the other side is that electrophilic carbon. All right, in this case, that was in the middle of this 3-carbon chain here. So I need to put another 1, 2 carbons on here. And then lastly, my carbon-oxygen double bond has turned into a carbon-oxygen single bond, or a hydroxyl group, an alcohol group on that carbon. So here's my aldol product here. Again, I've linked together the alpha carbon of one and the carbonyl carbon of its neighbor. All right, one more I want y'all to do, just for the sake of practice here. Let's use an even bigger and uglier ketone into cyclohexanone. All right, take that cyclohexanone, treat it with some base, and y'all are going to give me the aldol addition product. Okay, remember we're going to start by drawing 2 of them. And we're going to identify our nucleophilic site and our electrophilic site so that we can see how these things are going to be linked up here. So I'm going to start by redrawing that nucleophile. I'm going to put in my new bond, which means what's got to live on the other side of that bond? My electrophilic carbon. All right, my electrophile is in this, my electrophilic site rather, is in this 6-membered ring here. So I'm going to draw my other 6 carbons in that ring. All right, and then I also have to include that oxygen bonded to that electrophilic site. Point it down here just to give it some more room. That alcohol group. All right, count carbons. We should have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we also want to double check those spacing of our functional groups. They should be 1, 2, 3 carbons apart. All right, so these double checks that we have for our aldol addition products. Cool. All right, so if that's an aldol addition, our next reaction is what's called an aldol condensation. All right, this is when you do an aldol addition followed by a dehydration of that aldol. All right, let's use our same simple 2-carbon ketone here, or rather aldehyde. And we use very similar conditions for our reaction here. We also use these basic conditions. We just also apply heat. All right, so an aldol addition would be just basic conditions. An aldol condensation is going to be our basic conditions plus heat. All right, so then what do we do here? What is our product going to be? Okay, importantly, since we just did this mechanism, I'm not going to redo it here. I'm just going to note that that first step is that aldol addition. All right, so we have that same aldol addition product. All right, so then what's going to happen here, okay, so first of all, let's just note that in our product, we also have an alpha carbon. All right, it's still an alpha carbon because it's located right next door to that carbonyl carbon. And what did we say about alpha carbons in basic conditions here? They are acidic. All right, so what's going to happen is yet another one of our alpha hydrogens is going to be removed by our base. Okay, so again, we have our carbon with its negative charge. But here's the big difference. It doesn't act as a nucleophile Instead, this pair of electrons comes down and kicks off this hydroxide as a leaving group. So everybody take a second. Following my electron pushing arrows, what is the product of this aldol condensation reaction? All right, so following those electron pushing arrows, I don't have that carbon-oxygen single bond anymore. Instead, my lone pair came and formed a carbon-carbon double bond. So this is my condensation product. We did an aldol addition followed by a dehydration where we lost H and OH, or the equivalent of a water molecule. All right, now let's focus on this last step here, because we spent the previous chapter talking about alcohol groups, right? And we made a big stink about these hydroxyl groups being what? Good or bad leaving groups? Yeah. Bad leaving groups, right? We made a whole big stink about it. We had all these methods of dealing with this terrible leaving group. And then we got to this chapter, and I'm like, hey, look, it's a leaving group. And you're like, what the heck? We just made a whole stink about how it isn't a leaving group. So why are we allowed to have this OH as a leaving group here? Okay, so this hydroxide here, we're going to note it is a bad leaving group. All right, but in this case, it does actually leave. Why? So, two reasons. All right. Number one, our product is this super duper stable product that we have here. And what is it about our product, our condensation product, that makes it so super duper stable? Yeah, and we had a special name for it when it was that perfect spacing. They're conjugated, right? So why are we getting this super duper stable product? Because we have this conjugated set of pi bonds here. Because of our mechanism, our carbon-carbon double bond will always be located in that perfect spacing away from that carbonyl bond, so it is conjugated, all right? So, bad leaving group, but number one, we get this super stable product. All right? And the other thing is, since we have that bad leaving group, all right, so super stable product, okay? But the other thing is our reaction conditions here. There's heat. So we have a lot of energy to overcome those high activation energy barriers. That high heat allows us to kick off that bad leaving group. All right, and then it's a steep downhill in terms of free energy, because we get that nice stable product, our conjugated pi bonds. All right, so hydroxyl groups, bad leaving groups. In this case, we're going to say, see it still play the role of a leaving group because we have that high heat and we get that nice stable product. All right, so then, given what we did over here, we did practicing our aldol addition products. I'm going to take these same sets of substrates here. And now, instead of just sodium hydroxide, we're going to add sodium hydroxide and heat, our condensation reagents. So everybody take a second. You did the aldol addition product. Give me the condensation product. All right, we got that double check of counting carbons. All right, the other thing that we can note here is in our condensation product, since our carbonyl group and our new carbon-carbon pi bond are conjugated, we see that same 1, 2, 3 carbon spacing where your double bond is located between carbons 2 and 3. So again, just double check your products, making sure they have the correct number of carbons, but also those two functional groups have that correct spacing. All right, so starting out here, here's my addition product. All right, but now we have a dehydration, so our functional group spacing, 1, 2, 3 carbons apart. Now we should have a carbon-carbon double bond between carbons 2 and 3. All right, I'm going to kind of redraw this methyl group, point it in a more natural direction. Cool. So here would be my aldol condensation product. All right, same thing here. So again, we can start by redrawing that nucleophile. We're going to draw our new carbon-carbon bond to our electrophilic site. All right, we got that 6-membered ring here. And I have my new carbon-carbon double bond, all right, between carbons 2 and 3. All right, my nucleophilic site and my electrophilic site now has that carbon-carbon double bond. Cool. All right, so aldol addition and aldol condensations. We have aldehydes and ketones reacting with their neighbors. All right, one of them playing the role of the nucleophile after that base creates an enolate ion, and the other one playing the role of an electrophile at that electrophilic carbonyl carbon. Okay, when we do a condensation and we add heat, we get that same aldol addition product, but then there's this subsequent dehydration step to create our conjugated pi bonds here. All right, and one more for today, what's called a Claisen condensation. All right, even though it's got condensation in the name, this is more analogous to an aldol addition reaction. I'm going to do an aldol addition, but instead of using aldehydes and ketones, we're going to use an ester. All right, so first of all, let's remind ourselves what the heck an ester is. An ester, we have this carbonyl group, but bonded to my carbonyl carbon is an oxygen atom. All right, and not an OH group like a carboxylic acid, but another alkyl group on the other side. So this would be an ester here. All right, this Claisen condensation is also catalyzed under basic conditions, and for right now, I'm just going to leave it as base. We'll talk specifically about the base that gets used in these reactions in a second. All right, and our first step is going to be this acid-base step, a proton transfer. Just like aldehydes and ketones, where's my acidic site in this molecule here? That alpha carbon. So let's just note esters also have alpha carbons. And just like with aldehydes and ketones, since those alpha carbons are next door to those carbonyl carbons, they are relatively acidic and can be deprotonated. And so my first step here is my base, and again, I'm just going to leave it as generic base for right now, or B with a lone pair is going to deprotonate my ester. All right, specifically that alpha carbon. All right, so here we go. This thing here, now being deprotonated. Got as a lone pair, negative charge. And it's going to play the role of what, do we think, in the next step? Nucleophile or electrophile? Nucleophile. And just like in our aldol reactions, our electrophile is going to be just another ester molecule that's floating around. And what do we think that electrophilic site is? That electrophilic carbonyl carbon. All right, and what do nucleophiles do to electrophiles? They attack. All right, so thus far, exactly analogous to what we saw with our aldol addition reactions. If I'm going to draw my product of this step in my mechanism, I'm going to start by redrawing those carbons of my nucleophile. Try to make a little bit more room for myself here. All right, so then when I draw that new bond, what's going to be on the other side? That electrophilic carbon. All right, everybody finished drawing my intermediate here based on what we did before? So that electrophilic carbon had a carbon on one side and an oxygen on the other side. That oxygen, because we were an ester, had its own alkyl group on there. And then, of course, we still have that carbonyl oxygen. Carbonyl oxygens accepted that pair of electrons, becoming that negatively charged alkoxide ion. All right, so up until now, exactly like what we saw for our aldol additions. The only difference is we started out with an ester, and we did the same thing that we did with aldehydes and ketones, where we deprotonated that alpha carbon, and then one ester attacks another one. All right? The big difference is going to be what happens at this step here with this particular intermediate. First of all, we talked about, we have a special name for these intermediates when our carbonyl carbons get attacked. Your carbonyl was a trigonal planar, and now that it's got these 4 bonds, it's got a different geometry. What do we call these intermediates? Our tetrahedral intermediates. All right, but different from when we had aldehydes and ketones, our tetrahedral intermediates over here, these were stuck. And there was nothing that we could do until we protonated that oxygen to create our alcohol group. What we're going to see for these other carboxylic acid derivatives is that these tetrahedral intermediates are not stuck. Instead, they always have some electronegative element that's bonded to that carbonyl carbon. And so these are tetrahedral intermediates with leaving groups. All right, where that ester oxygen and its alkyl chain are going to play the role of a leaving group, allowing this pair of electrons to come back down, kicking off that leaving group. All right, so everybody take a second and draw me my product of these Claisen condensation reactions. So in this case here, I have my new carbon-carbon bond from my nucleophilic site to my electrophilic site. All right, but now I've reformed my carbon-oxygen double bond when we kicked off that leaving group. All right, so in our Claisen condensation products, it's not an aldol anymore. Now we have these two carbonyl groups. We can note, though, that they are always going to have that same 1, 2, 3 carbon spacing that we saw before, because we still have our alpha carbon reacting with an electrophilic carbonyl carbon. All right, and I said that we were going to talk about our base that we use for these reactions. So importantly, let's note that our other fragment here, our leaving group that gets kicked off, is one of these alkoxide ions. And these alkoxide ions here are themselves good bases. So when we do a Claisen condensation reaction, we use a base that matches that ester leaving group. So in this case here, my base that I would choose for this specific reaction would be sodium methoxide or those methoxide ions. All right, the sodium's not doing anything. Okay, so then let's say that I wanted to do a Claisen condensation. Using this ester here. All right, everybody take a second and draw in the base that we would be using for this reaction. Our base needs to match that leaving group of our ester here. So in this case, I would use sodium F oxide, or we could just draw in an F oxide ion. Okay, take a second to draw our product of this Claisen condensation reaction. All right, again, it's helpful to draw two molecules, reminding yourself that one is going to be playing the role of the nucleophile at its alpha carbon, the other one the electrophile at its carbonyl carbon. draw my nucleophile. I'm going to draw a new bond off of that alpha carbon. On the other side must be that electrophilic carbon. All right, importantly, this electrophile is going to lose that leaving group. So my product here will actually have slightly fewer carbons. I'll only have these 4 carbons from my electrophile. So here's one of them. Here are the other 3, so here's my 4 carbons total. And that oxygen on that electrophilic carbon, the difference in a Claisen is that it's reformed as a carbonyl, a carbon-oxygen double bond. So here's my Claisen condensation product. And again, we can double check our spacing of our functional groups should be those 1, 2, 3 carbons apart. All right. So my final product here has all 1, 2, 3, 4, 5, 6 carbons from my nucleophile, but then it has my electrophile minus that ester leaving group, or only 4 carbons from that electrophile. Cool. All right, we're going to pick up with this next time.